Grade 12 Physics, Dynamics, Note number 2, Projectile Motion. In this note, we're going to review some of the projectile motion aspects you would have learned in grade 11, and we're going to apply them to some problems at the end. So for projectile motion, remember we need to make two assumptions. Number one, we have acceleration of g, which is 9.8 meters per second squared, which always points down. And number two is we're always going to ignore air resistance. So what we need to remember is that an object in a projectile motion makes the shape of a parabola. So let's examine what that parabola looks like, and in particular what the x and y components of the velocity look like. So let's say we have a ball thrown into the air here at different time intervals. That's where the position will be, those black dots. First, let's look at the x components of the velocity. And what we should remember is that it's a constant velocity, so they should all be the same. So when drawn, we can see that every single x component of the velocity is the same length. Which means the spacing intervals, the x spacing intervals of those dots would always be the same as well. The y component we know is affected by gravity, so it's going to start out pretty quick, but gravity will slow it down. At the top it won't have any y component, and then as it goes to the second half of the arc it's going to speed up. And that's shown by the changing size of that vector. It gets smaller, 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 bigger, bigger, bigger. So if we look at the overall, we're going to add those two vectors up. That's denoted here by the black arrows. We can see that the black arrows trace out the parabola of that curve. The velocity is always tangent to the parabola. Alright, so moving on, we can make a summary of what's going on. We have to remember that the horizontal and the vertical components are completely independent. Any change of the vertical component has no effect on the horizontal component whatsoever. So because of this, we should always solve for time first in the problems. Time is the only link between the two motions. The time taken to travel the x motion would be exactly the time taken to travel the y motion. So we can do an example, if you remember this from grade 11 class. Let's say we have some sort of a stand with two balls on the top, one that's going to drop straight down, that's the striped one, and the hollow one is going to be flicked out to the side at the exact same time that the first one is dropped. We're going to notice that they're both going to be dropping at the same rate, so after 1 second, 2 seconds, 3 seconds, they're falling, except the hollow one is also going to move out to the side. So looking at the vertical components of their velocity, we can see that they're exactly the same. So if they have the same velocity in the y direction, that means they're going to hit the ground at the same time. And because the Vx is totally independent of the Vy, it doesn't matter how much it's flicked out to the side, they're both still going to hit the ground at the same time. Again, looking at the overall for that V component, the overall is going to make the shape of a half parabola. The overall component for that first ball is just going to be that y component. Moving on to an example. Let's say we're on the top of Niagara Falls, 65 meters high, and you're inside of a barrel and you're going to go off the edge of the falls at 12.5 meters per second. We're going to try and calculate the range or the distance away from the bottom of the falls that you're going to hit as the barrel lands in the river. So given these conditions, how far from the base of Niagara Falls does the barrel land? Remember, what we need to do in these problems is we need to solve for the time of flight first. So to do that, we know that the barrel is going to travel along that dotted line, but it's pretty difficult to do the math. So instead what we're going to do is, let's pretend that something is dropping straight down, and let's do the math on that to find the time of flight. We know if we're going straight down, that initial velocity would be 0. The acceleration is negative 9.8 meters per second squared. The distance we're traveling is negative 65 meters, so let's solve for the time. We're going to use this equation here, but knowing that initial velocity is 0, that first term is going to go away. So let's rearrange for time. We'll insert our numbers, negative 65, 2 times negative 65 over negative 9.8, which gives us 3.64 seconds. So knowing that's our range, knowing that's our time, we can find the range. So we're traveling at 12.5 meters per second in the x for 3.64 seconds, which gives us a range of 45.5 meters. Second example here, this would be new for grade 12. Let's say we shoot an artillery shell off of a cliff, but we shoot it at some angle above the horizontal. It'll be going at 65.5 meters per second on a 15-degree angle above the horizontal. And let's say the cliff is 50 meters high. So an artillery shell is fired like so. How far from the base of the cliff does it land? So we're going to take the same steps as we did in the first problem, except we're going to have to see what the angle entails. So first let's look at time. Instead of going along that parabola, again, we're going to look at something that goes straight up and then straight down, because we'll know they'll both hit the ground at the same time. So we need to look at whatever that y component of the velocity is to begin with. So if you build a triangle that's the opposite side of the triangle, it's going to be 65.5 sine 15, which gives us 17 meters per second up. Again, the acceleration is negative 9.8 meters per second squared down. We're going to travel a displacement of negative 50 meters, so let's solve for time. Using that same equation, we can insert our numbers. But we notice here that there's two t terms, there's a t and a t squared. So unfortunately that means that this is a quadratic, and we're going to need to use the quadratic formula to solve for t. So let's rearrange it into standard form, like so. And then using the quadratic formula, where t equals negative b plus or minus the root of b squared subtract 4ac over 2a. Putting the numbers in, remember, if there's a negative, we have to keep that negative attached to the number. When you compute this in your calculator, we should get 5.37 seconds. The other answer to the root will actually give us a negative overall answer, and we cannot have a negative time. So finding the range, we now need the x component of that velocity. So 65.5 cos 15 times the time that we found. That will give us a range of 340 meters. Final example here is, let's say a military shell blows up in the air 4.4 seconds into the flight. We're going to try and calculate what height and what range this occurs at. So this one's a little bit different because the time is given right off the bat. We're going to have to know what to do with it to solve for what we want. So let's draw a picture here. So there's the projectile leaving. It's going to go at 30 meters per second on a 55-degree angle. And sometime into the flight, 4.4 seconds, we get an explosion. We want to find the range, and we want to find the height it happens at. The easier part to start with is the range. We know that we have a constant velocity in the x direction. So all we need is the x component of the initial velocity, which would be 30 cos 55. And we know it's going to travel for 4.4 seconds. So let's add that in. So we get a range of 75.7 meters. Now let's look at the height. Again, all we need to do is look at the vertical motion. Pretend we throw a ball up in the air. We're going to find what height that ball is going to be at 4.4 seconds. So here, we can list what we know. The time is 4.4 seconds. The acceleration is negative 9.8 meters per second squared. The velocity is going to be the y component, so 30 sine 55. We're going to look for how far in the air it's going to be. Let's use this equation. So we're going to add in what we know. And what we find is we get a final distance of 13.3 meters.